Hello everybody, welcome back to Arduino for Amateurs. This is episode number 16, Analog Sound Sensors. As always, my name is Matt Gracie. I'm a hacker from Buffalo, New York. I'm a member of the Bidhaven Hackerspace. And what I'm going to be talking about in this video is using an analog sound sensor as an input for your Arduino. In the last couple episodes, we talked about digital sound sensors. And digital sound sensors, like all digital means of input, are capable of producing ones and zeros, right? So a digital sound sensor, you set a threshold using that adjustment screw, and if the level of ambient noise in the environment is above that threshold that you've set, it produces a 1. If it's below, it produces a 0, right? It's a binary value, ones or zeros, that's it. An analog sound sensor is a little bit more nuanced. Like all analog devices, it's able to produce a variety of values. So you don't just get there is sound or there is not sound, but you get a relative reading on the amount of sound in the room. This is technically a microphone, but it's not capable of doing anything like voice recognition or deciphering what's being said or even recognizing particular sounds. But what it can do is it can give you a reading on the magnitude of the sound. So you can use it as an input to a circuit to change outputs or change values depending on how much noise there is in the environment. So if you want to build something like a light that gets brighter as it gets noisier in a room, right? That would be a good fit for an analog sound sensor. This is the sensor that I'm going to be using. I bought a 5-pack of these off Amazon for a couple dollars. It does look similar to the digital sound sensor. This one actually does analog and digital. The biggest difference is it's got 4 pins at the bottom here instead of just 3. So you may recall the digital sensor had a digital out pin, a power pin, and a ground pin. This one has digital out, it's got power, it's got ground, and it's also got analog out. So we can use this as a digital or an analog sound sensor, right? We can either have it set up with a threshold or we can have it measuring magnitude. Just like the digital sound sensor we used in the last couple of videos, this also has this adjustment screw here for setting the threshold if you're using it in digital mode. Doesn't seem to do anything in analog mode. I twisted it around with a jeweler's screwdriver and it didn't change any values. But if I'm understanding that wrong, please feel free to correct me in the comments. Up here at the top, we have a microphone, just like the one on the digital sound sensor. This is a very simple sound receiver. Again, it's not going to let us do voice recognition or anything complicated like that. It's just enough to measure how much noise is in the environment. All right, so this is the circuit that we're going to be working with in this video. Over here, this is a piezo buzzer. So this generates noise based on how much power you run through it. We're not actually going to be using this today. I was just kind of playing around with that next to the sound sensor. Here we have the sound sensor itself, and this is a top view of that microphone. It's a black circle, just like the one on the digital sensor. And as always, we've got our power coming out to the red rail, coming out to the power rail. We've got our ground coming out to the ground rail here. Those are both hooked back to the Arduino into the 5-volt and ground pins on the Arduino to the end of the rails here. And then we've got this orange wire. This is going to A0, to the analog input on our Arduino. Over here, we've got our old friend, the NeoPixel ring. This is hooked to power and ground, and it's also hooked over here to pin 7, the digital output on the Arduino. So we're going to use this as an output device that reacts to the amount of noise coming into this. Okay, so this is the basic circuit that we're going to be working with. The analog sound sensor plugged into A0, and then the NeoPixel ring plugged into pin 7. So let's start with a very basic demo of how an analog sound sensor works. So this is our Arduino IDE. This is a sketch that I wrote for this video. We start by defining the sound pin. That is, what is the pin that our analog sensor is plugged into? It's plugged into A0. We have an integer value. We call that sound value. And then the sketch itself is very simple. The only thing we do in setup is we set up a serial monitor because we want to be able to read the value off the sound pin. That's the simplest thing. And then we have a loop. Our sound value is set to an analog read of the sound pin. Then we print that value to the serial monitor, and then we delay for 1 second. So if I clear the output here, you'll see my serial monitor is putting out 218, 218, 217, 217. So that's the analog reading of the ambient noise in the room. You'll notice as I talk a little bit louder, my numbers go up there. If I take my analog sound sensor here and I blow down onto it like I did with the digital sound sensor, you see I've got a 877 in the middle there, and then it goes back to the 200s. 340, and then it goes back down to the 180, right? So it's not super precise. But what that's doing is it's showing me that the sensor is picking up the ambient noise in the room, and then it is giving a higher analog value for that reason. So every 1 second, we're checking in on the microphone, and then it prints the value of that exact slice of time, that very instant when it goes to the top of the loop. So that's one way that you can use the analog microphone, right? You can have it sense the ambient noise in the room and then go on and compute and do all the other stuff. But as you can see, it's not super consistent. Even when I'm making noise, if I don't do it at exactly the right time, the value doesn't change, right? So if I'm trying to make something that's responsive to the environment, I might want a little bit more capture, right? Instead of capturing it every second, maybe I want to capture it more often and then use the highest value. So let's check out this next sketch. This next sketch, as you can see, it's called Analog Sound Sensor 1 second blocks, and that's exactly what I did. It starts off the same way. It defines the sound pin A0. It has the sound value integer. It sets up the serial monitor. But now, instead of just reading it once and then delaying for a full second, you see we've got a loop here, a for loop for int I equals 0, int I is less than 20, I plus plus, so increment I each time, 0, 1, 2, 3, 4. We've seen for loops. And then we are going to have an integer we call temp reading, which is just a temporary integer. That's why we're declaring it here in the body of the for loop. It doesn't scope outside of this loop. Temp reading is set to the value of our sound pin. If temp reading is greater than the current sound value, then the sound value is sent to temp reading. Then we delay for 50 milliseconds and then go back up to the top. What is our effect here, right? What does this actually do? Well, instead of taking one sample per second, so we take a sample, we delay for 1,000, we're taking 20 samples a second and we're using the largest value, right? So this way, if there's a noise, but it doesn't occur in between that 1 second tick-tock that we had in the last video, we'll still capture it because we're increasing our sample rate, right? We're taking 20 samples per second instead of just one, and then we print loudest reading and the value of the sound. We get to the bottom of the loop, we set sound value to 0, we go back up to the top, and the whole thing starts again. So now, if I turn on my serial monitor and I upload my sketch, okay. So now my loudest reading is 232 because that's the ambient noise in the area. If I blow into this, you'll see it goes up a lot more consistently, right? It goes up into the 800s and stays there and then goes back down to the 200s for the ambient noise in the room. And this is a room full of computer fans and electronic junk, so it's not surprising that there's at least a little bit of background noise. So this is a way that programmatically we can overcome that issue, right? Instead of just sampling once per second, we sample more times per second, and then we return the largest value. If we wanted to, depending on what our purpose is, we could return the lowest value. We could return the average of the 20 values. We can manipulate that any way that we want. The important lesson here is that we're taking a bunch of samples and then returning an aggregated value instead of just taking one sample per second. So that's two examples using this serial monitor. And then one last example that I want to show you. Oh, I don't need Open Recent. I just need my code here. I mashed together that analog sound sensor 1 second block with the NeoPixel ring tachometer that we saw in an earlier video. So let me walk through this code a little bit, and then I'll show you what this one looks like. This time, in addition to the analog sound sensor, we're also using a NeoPixel ring. So we start by including that NeoPixel ring library. We define the pin that's plugged into the ring, that's pin 7. We define the number of LEDs in the ring, that's 16. We defined our sound pin, that's A0, right? So we've got our analog sound sensor plugged into A0. We've got our NeoPixel ring plugged into 7. We have an integer value, we call it map dial value, that's set equal to 0 initially. Then we instantiate a NeoPixel ring object, 16 LEDs, plugged into pin number 7. We're encoding it in GRB and 800 kilohertz. Then we have another integer value called sound value, right? And sound value, just like in the last video, sound value is the analog value being produced by our analog sound sensor. Our setup stanza here has gotten a little bit more complicated because we need to do all the NeoPixel stuff. So we turn on our NeoPixel object, which is named Pixels. We set the brightness, we clear all the values in it, and then we show. So we blank it, and then we turn it on, make sure everything's okay. We're also going to turn on our serial monitor, right? I don't think we actually really end up using the serial. Oh, yeah, we do down here in this other function. Now we get into our loop. So we turn all the pixels off. That's the first thing we do. And then we call this function called getSoundLevel. So I'm going to move down to that function, and then we'll come back up here. What happens in getSoundLevel is we're running that analog sound sensor 1 second block code. We do our for loop. We take 20 samples. We delay by 50 milliseconds between them, so this takes 1 second to run altogether. Then to the serial monitor, we print the loudest reading and the sound value, and then we come back up here. So by the time getSoundLevel is done, sound value is set to the largest value that the analog sound sensor detected in the last 1 second. So sound value here can have a value between 0 and 1023. We use map to map sound value onto a 0 to 16 range. So we go from 0 to 1023 to 0 to 16. Should probably be 0 to 15, but whatever. And we set that integer map dial value to that value. So this will be somewhere between 0 and 16. Then we run a for loop. And this is a little bit complicated. You may remember we did this with a potentiometer before. So we start with I equals to 0, and we say I is less than or equal to map dial value. So this is going to run, and it's going to count from 0 up to the proportional value of that analog sound sensor output. So if the analog sound sensor value gets mapped to 12, it's going to run from 0 to 12. If it gets mapped to 3, it'll run from 0 to 3, etc. Right? So what we're doing here is we're filling in LEDs on the ring from 0 up to map dial value. If I is less than 8, that is, if this is one of the first 8 LEDs, then we are going to set the pixel color to green. Red, green, blue, 0, 255, 0. Full value for green, nothing for red or blue, so that means green. Else, so if it's not less than 8, else, if it's less than 13, then we set it to yellow. That's what you get when you max out red and green. Else, meaning if it's not less than 13, it's 13 or more, we're going to set the pixel color to red. So this is going to give us sort of a tachometer view, right? It's going to start off green, then yellow, then red as we go around the dial. All of those values, we're not doing it with an array like we did in the last video. We're writing it straight to the pixels object, straight to the NeoPixel ring. And then once all those values have been pushed out to the ring, then we run pixels.show to update it. We delay 100 milliseconds, and then we set our sound value to 0 and go back to the top of the loop. Okay. So what we're doing is we are taking all of those samples, we're taking the largest value in them, we're filling in a corresponding number of NeoPixel ring lights, and then we are going back and doing it again. So let me I'll do the serial monitor, and then I will upload this to the code, to the circuit. Clear this. Okay. You can see right here, I've got this green ring. If I blow into the microphone to make some noise, that spins it up. The louder it is, the more lights I can light up. So that's what the analog sound sensor does for us. Rather than just turning lights on and off, rather than just producing a 1 or a 0, instead it gives us a value between 0 and 1023, and we can key on that value and use it to produce a proportional output, whether it's making a noise or lighting up a string of Christmas lights or lighting up these NeoPixel rings or whatever we need it to do, right? We can change the output of the circuit based on the magnitude of the input coming off that analog sound sensor, rather than just having on or off like the digital one. Okay? Pretty cool. Like I said, these analog sound sensors, you can get them for $1 or $2 on eBay or Amazon if you want to play around with them. They're very cool. And that's all I have for tonight. So I will see you in the next video.